Hey there, hello, and happy Saturday. Welcome to some data science live streaming. My name is Carl, and I'm a data scientist in California. And I'm here to talk to you about some data science today. Well, not exactly, it is data science. It's definitely data transformation is what I'm going to talk about today, and dimension reduction is a very key part of data science. And hello, Crumb Blossom. Yo, cool Twitch tag, username, nice to meet you. Let me know if the volume's okay and everything's good in the audio. I'm actually taking a big step in my streaming career today. I finally got a proper microphone. Hopefully it actually makes a difference. We'll see. You let me know if it sounds any better, or I don't know, the levels look good. For all I know, it's not even working and no one can hear me, but I'll just keep going until someone says there's no sound. Anyway, my name is Carl, and I'm going to talk about some data science today. If you've seen my streams before, I usually start by just talking for a while to introduce the subject, but I'll get into some code very soon. And so I'll start at the beginning with some introductions. I'll tell you what a dimension reduction transformer is in just a few minutes. But first, I'll tell you what is churn, and what is this weird book cover shown here. What is churn? Churn is when customers or subscribers or users quit or unfollow or cancel you or your service or whatever it is you want them to do. If they're not doing it, that's bad, right? So churn is bad. And every company nowadays wants to reduce churn. All the biggest companies and all the smallest companies, they want recurring revenue from their customers, and churn is the opposite of recurring revenue. So it comes from the term called the churn rate. The churn rate is a metric of churn, which we're not going to talk about exactly today, although we'll look at a few churn rates, not how to calculate it. But anyway, it's the percentage of customers that quit. And it started from that, but churn is also now a verb, and you can say the customer churned, or even I'm churning. Most people don't say that unless you actually work in the business. You might say, oh, I'm churning from Netflix, I'm so sick of it. But usually you talk about churn in the third person, not the first person. But it can also be a noun, and you can even say a customer is a churn, or like make a churn report, or you know, something like that. Again, if you're in the business, if you're used to it, it's common to use it as a noun, a verb, and a churn rate, and I don't know, just a general state of the world. The world is in a state of churn, so no one will argue with that. Because churn means mixing or turning things over, which is why in that picture, well, let's look at that picture again. Here's that picture on Fighting Churn With Data. The picture is of a butter churn, which in English is kind of the most common use of the word churn. I don't know, classic use of the word churn. So I got them to put that picture on the cover of the book. And the book is the book that I wrote about my experience as a data scientist at a company which was like a subscription platform. And that platform is called Zuora. I don't work there anymore. It was great, but you know, can't stay at one job forever, especially in the technology business. So I've moved on now. I can tell you more about that later. But based on my experience at Zuora, where I did a lot of churn fighting, I wrote this book to basically help other people deal with churn more or better, or if, I don't know, if they never dealt with it before, just to deal with it. So that's what Fighting Churn With Data is, like the book. But what is Fighting Churn With Data really means data-driven churn reduction. So trying to use your data to reduce churn at your company, or your live stream, or whatever it is. I really like to talk to people about how you reduce churn from live streams, because I don't know how to get the data. I really got to look into that, since I'm supposed to be a data science stream. I don't know that Twitch would actually give you good data to actually do a good job on your churn. But I don't know. More about that later. Let's say, what is data-driven churn reduction usually for a company where you own your own data and product? Well, you make a great product first by using your data to figure out what people like and want in your product. And it's like a survey without doing a survey. It's a survey that everyone has to take, but there's only one question. It's stay or churn, but it gives you great insight into your product. Then you can use that data to drive your marketing campaigns, figure out how to send your customers useful messages and not annoying messages through email or pop-ups, whatever way you can communicate with them. And there's also customer success and support. Customer support, you probably know when you call in with a problem for a product. Customer success is a newer proactive form of customer support where you actually use data to figure out how to help your customers and do it proactively. You also might use your data to adjust your sales and pricing, right size your plans, but don't give discounts. Many people think that you reduce churn by giving discounts, but it's actually not a good way to reduce churn, because once your customers know that they can get a discount by just threatening to churn, then it undermines your pricing. So it's better to come up with a tiered pricing structure in the first place. So yeah, those are the main ways of reducing churn. We're actually not going to talk too much about these today. Today is going to be more like a technical exploration of using some churn data, but we'll get to that pretty soon. Oh, and also, by the way, shout out any questions. Sometimes midway through the stream, someone's like, what's churn? And I got to go back to this. But any other questions about anything, happy to get into it. So I'll just make my little sales pitch. Why should you care? It's a really common data science problem to have to use data to help with churn. But it's kind of unlike other data science problems. So it's worth learning some of the special techniques that I share in the stream and in the book. And also, if you're just learning data science, this is a cool way to do it, because you go from raw data all the way to using the data for results. Now, today, the stream is going to be somewhere kind of in the middle. It's more like processing the data, but it's important, and cool stuff for anyone who's actually into data and, doing this. So let's see. Oh, okay. This next section of the stream is something new I've been doing, and that is thanking my followers who joined me, like Simon1187S. Now following Simon, I hope you see this stream, maybe come back and visit and know I gave you a shout out. Don't worry, I don't have too many new followers. In case you haven't noticed, I'm not the most popular guy on Twitch, but I do want to give a shout out to the people who did, like Subo Brata1. Thank you for following me. Welcome to my little data science community, as it were. And next is a cool Twitch tag coming up as soon as this thing works. There we go, Blastwave. That's a good one. Thank you for following Blastwave, and nice job getting a cool Twitch username. And last but not least, since my last stream, we have one more person coming up. Haru Kakumi. Thank you for following, and hope you can join me and come back and see the stream sometime. So that's just my shout out to the new followers. I just like to do that at some point. I don't know when the best time to do it in the stream is, but maybe at the beginning. So now that I've talked your ear off with a bunch of chit chat and shout outs, where's some data? So the data we're going to use today comes from a simulation. Why a simulation? Because it's hard to get real company data to work with. Companies tend to be pretty private about their data and stuff. And if you know of any data from a company that has churn that I could analyze on the live stream, please let me know and reach out to me, have that company reach out to me. Most companies won't share out their data for analysis and training, which is what we're doing here. So that's why I made a simulation, which is very much like a real churn situation at a company. And that's what I use for demonstration and teaching on the stream. So let's look at some data. Let's see. If you've set up, and I'll talk more about the setup in a minute, you'll have this data in your database. I'll tell you how you can get it in a sec, but I'll just show you what we got here. I mentioned it's a subscription data set. So there's a subscription table, as you can see here. There's an account ID, which identifies the customers. I'll say more about that in a moment. And Customers have multiple subscriptions, which are actually what we call coterminal, in that the end date of one subscription is the start date of the next. And you can tell when a customer churns because their sequence of subscriptions runs out. Like this guy churned on June 15th because they have no more, 2020. So it's an old simulated data set. I mentioned it's simulated, it's not real data. So it also includes a table of account data, which actually looks like real personal data. Like, ooh, is this really someone's birth date? No, I generated it in a simulation. No PII was used anywhere in my book or anything like that. But I did do a simulation to show you what some real PII data might look like. In this case, a sales channel, which means what channel they use the product through. I'm saying App Store 2, App Store 1. Well, there's 2 app stores you might have heard about, but I'm not naming them because I don't have the rights. And a country. So anyway, so that's the data available about who the customers are. But the more interesting thing is what the customers do. So there's a table called event, which actually doesn't look that interesting. I'm just going to make a pitch for why this is interesting. And now it doesn't look that interesting. It's just a bunch of account IDs, times, and events. But let's see, I can join the events with the event type table, which I'll try to do right now. On, let's see, I guess that e.event type equals t.event ID. Let's see if this looks right. Yeah, I didn't think that was right. I think this should be like event type ID or something. There we go. So now I've joined this with descriptors of the events. Let's order them by event time to make it look a little bit more interesting, because this is showing them ordered by event type ID, which shows only one type. Okay, now I've ordered them by event time, and you can see that these events are instances of posts, messages, likes, ad views, more likes. So this sounds like a social network, like I mentioned earlier. It is a social network simulation, and these are generated events for each customer. And the way the simulation works is that the customers are generated, they perform these events, and that gives them utility or enjoyment of the service. And if they get enough enjoyment from the service, they don't churn. Because remember, they're paying $9.99 a month. If I go back to my, going back to my subscription query, remember, $9.99 a month is not free. So people have to get enjoyment from it to keep using it. And the amount of enjoyment they get is determined by, whoops, wrong one, is determined by how much of these events that they do. So that's the data set that I'll be using throughout the stream. And we're going to see these events again in another form, because after you have events, you calculate what I call customer metrics, but what a data scientist will also typically call a feature, a feature is the common term. I like to call it customer metrics for churn, because you're usually working with a customer success department or some business people who get confused if you use the term feature for something, a measurement in your data. But you join these events together and make measurements of the customer in a data set, which I'll show you in just a minute. Let's see. Let me go back to the script, see what I was supposed to say next here. That was the first data and coding. Just so you know, I won't go this whole time just talking. This is not a just chatting stream. This is a coding stream. Thank you. A little punchy today, sorry, but I'm in a good mood. Hope you all are too. All right, so this is the setup. If you want to get the code and actually run the code that I'm working on, you can do that. You do need Postgres and Python set up, and typically you'll clone the repo, although there is an option to pip install it, although then it's harder to actually look at and modify the code. Easier to run it, harder to look at it and modify it. And you do have to generate that data from the simulation. That can just take a few minutes if you do a small data set. But so I'm actually been working in a branch. I think I have GitHub open in my browser already. My last branch, I'm in a branch, which I should have noted. I go by dating my branches. This is 2021-0911, and it's a transformer branch. And I've had 7 commits that I've been making the last few weeks. So yeah, so that's where you can see the code. That has all the code from last week, and I'm going to do some new coding today. Okay, so that's the setup. Just got to throw that in the stream somewhere. So I think let's first talk about the data. This is a table which summarizes the data set that we'll be working with. And if you can read the fine print on the screen that you're looking at, you can see that it consists of features or metrics which are summaries of those events we were talking about. So you have like per month, new friend per month, and post per month are all things that a customer will do. And then we have all these other events, or rather metrics about them. Other things which are ratios, like ad view per post or like per post. And new friend percent change is how much your new friending behavior has changed, because that can be a really important churn indicator. Like if someone's new friends, dips, then they might be canceling from a social network. Or the days since someone had a new friend also. So those are the type of things we looked at. The first row shows is churn is 5%. So that means 5% of the customers churned in this data set. So I think instead of continuing to talk, maybe I demo how I actually get this overview. I think that's what I was supposed to do next. And this will just be a quick code example because we're going to do a lot more later. Okay, so this is showing you, listing 5.2 from the book. When it says that, it means chapter 5, listing 2. That's how it's organized in the book. But you can get all the code for free on GitHub. So this is, like I said, just going to be a quick review to kind of get you used to the framework that I'm using. So later on, I'll go more quickly. So this is the listing called Dataset Stats, and I think I'm ready to run it. So I can just hit the go button here, the debug button, so it'll stop at my breakpoint. And the parameter is a dataset path, which is a path to a file of data that we generated previously. So the first thing I do in this little script is check that the path is good and it's a file. Then I open it using pandas. In this case, the first 2 columns of the data count as the index. That's just the way this data set is created. But we can take a look at it in the development environment that I'm using. That's a lot of numbers showing up, but this is a better picture. You can use this view data frame functionality. And so this was what I was talking about. The first 2 columns form the index. That was the customer ID and the date. And then these other columns are those metrics that I was just telling you about, like per month, new friend per month, and what have you. So that's the data set we'll be working with. The first thing we do here is turn the churn column into a float to take that measurement. And then I use the key trick of this whole listing, which is the pandas describe function. And then, I flip it, transpose it sideways, and then I can show you what it looks like. And it looks practically like the result I was just showing you. So now I've got the metrics on the rows, and in the columns I have all these measurements. So this is a great trick to get a quick summary of a data frame. Unfortunately, as great as it is, it wasn't quite good enough for me. So the whole purpose of this listing is to add a few things to the describe function. And that's the skew, which is a measurement of how unbalanced a distribution is around its mean. The kurtosis, which is a measure of how much of the distribution is in the tails or away from the mean versus clustered around the mean. And then I also like to look at the first and 99th percentiles and the percentage of metrics which are non-zero, which is shown here. So at this point, I guess at this line I just reorder it. One of my favorite songs that's actually copyright free, gotta say, Suburban. Why use customer ID and date instead of just customer ID? Question from Crumb Blossom. The reason is because in creating the data set, I actually observe the customers on multiple times. So I don't just make one observation of each customer. We can actually see it in the, I don't know how we'll best see it in the data because I'd have to sort it. But so each customer will appear more than once, because you don't just observe them when they churn. It's also good to observe the customers each time they renew. And I go over this in more detail in the book, but basically you should observe a customer every month, if it's a month, assuming a monthly subscription. So suppose it's a monthly subscription. Then you should observe the customers every month. So you observe them every month whether they renew or churn. And then the churn rate in your data set will match the real churn rate of your business, which is good for analysis. So you don't have to do what I just said, which is observe the customers every month. But if you do, it has a benefit, which is that the churn rate matches your true churn rate. And then you end up with lots of observations of each customer, if they don't churn so long. So I end up with two columns which are basically identifying each row of observation. One the customer ID and the other the date. So, yep, that's that reason. It is a little bit different than some other kinds of data sets where you only will take one observation of each customer. But it's a good trick if you're concerned about the rate at which something happens. Anyway, digression there, but we love digressions. Because I basically finished this listing. After this, I'm just saving it out. So this was a very basic, not very interesting code listing. And I already showed you the results, which was right here. Let's see. This was the result that we kind of got out of that. And yeah. Well, anyway, I don't want to dwell on that too much, because that was really just getting started with what we're going to do today. So, let me have a sip of the good old coffee. And now we will sort of get into the main event for today, which is talking about scikit-learn, or I should say scikit-learn. You know, I realized that I was using sklearn where I was writing it, but most people write scikit-learn and say scikit-learn. Although, honestly, I hear a lot of people saying sklearn when they describe it too. I think someone needs to do a Twitter survey on whether they say sklearn or scikit-learn. Anyway, I'm a little inconsistent, which is a bad, habit for a programmer or developer. We should all be consistent. But anyway, so scikit-learn, a great package for data science, machine learning in Python. If you don't know it, we're going to be looking at some cool features of it today. One of which is the transformer, which is an object which represents a transformation in a data pipeline. So if you haven't heard of a data pipeline before, I'll back up and explain that. That means it's the series of transformations you have to make in a data set before you do whatever it is you're going to do, is what you're going to call your data pipeline. And yeah, sklearn provides this object framework for creating, defining transformers that also allows you to chain them together. There are some off-the-shelf transformers, but of course, stubborn old fool that I am, I don't use the off-the-shelf transformers. I had to make my own data processing algorithms. And in particular, there's two data processes in Fighting Churn With Data that are suitable for this. One is scaling data to scores, and the other is dimension reducing the data. We'll talk about both these today. Scaling data to scores is going to be like a review, because I actually did that the last 2 weeks. So we'll do a quick review of scaling data to scores and the transformer that goes with it. And then we'll talk about dimension reducing data with a transformer, which is the main subject for today. Okay, so there's the little background on what we're doing. What did I say next here? Okay, we'll talk first about scoring. So this is the concept of scoring shown with my kind of dorky picture. But what the problems with some data is that it's all clustered together, but with a few outliers. And this is very true of customer data for real products and services. It's skewed and has a lot of data in the tail of the distribution, however you want to say it. What that means is a lot of people have a low metric close to your average. In this case, maybe the average is probably like 25 or 30. But then you have a few really extreme outliers. Actually, I don't know if the average would be 25 or 30 in this case because it's a small sample. But you see this in the real data we looked at a few slides ago. Actually, let's do that and make the point. Let's take the like per month metric. The average is 90 likes per month. So this is a pretty active social network, 3 likes a day. But the maximum that we see in the data is 2394 likes in a month. Now that is someone who likes a lot of stuff. Could even be a bot, you know, but no one said there's no bots in this social network. So, and you never know in your real product. So there's some really extreme outliers, but most people are close to the mean of 90. And that's kind of represented in this picture here. But so that can be hard to analyze. So scoring is converting the raw metrics to an evenly distributed scale. In particular, you usually use 0 mean, 1 standard deviation. And you spread out the data so that it's evenly distributed. Well, typical normalization, you just handle the mean and standard deviation. But I teach a kind of normalization or scoring which also handles the distribution because it makes it easier to work with for some important applications, which we're going to look at. So this is the concept of scoring. Last week we talked about what I call a fat tails scoring, and fat tails means distributions with extreme data. So I'm kind of switching to calling that extreme data scoring, and I'm going to use that term also. The original scoring formula I teach in the book is to take the logarithm of 1 plus the metric, and then you subtract the mean of the transform metric and divide by the standard deviation. This is good, but it only works for metrics that are at least 0. As you see here, you take the log of 1 plus the metric, but you can't take the log of a negative number. It's not defined. So that's why you add 1, and then it works for 0, but not for going negative. So because we're going to do percent change in one of our features, let's go back to the data set. We do have a metric which goes negative, which is the percentage change in new friends. I should have mentioned that when we were looking at this data before. Percentage changes can go as low as minus 100%, because that's if you go from some number to 0, that's a minus 100% change. And any reduction in the number of new friends will result in a negative value of the metric. And this is just one example. In real data sets, you might have a lot of metrics which can go negative. This is sort of a simple example data set, to be honest. But so that's why we need to handle negative values, and I introduced this more complicated formula, which is the log of quantity, the metric plus the square root of the metric squared plus 1. And it seems like a mouthful. It's actually something called like hyperbolic tangents. I actually forget. It's one of those really weird trigonometric functions you might have heard about in college sometime, but no one really knows what they're for, myself included. But this one is good for transforming your data. If you have a negative metric, then this m squared will be positive, and then you add 1 to it, and it'll be just a little bit greater than this negative metric in the m variable here. So this total will always be positive, and the more negative it is, the closer it will be to 0. So this is suitable for scoring data with extremes in both directions. So that is the transform. And now I'm going to mention again how the scikit-learn transformers work. And if you're wondering why it's sklearn versus scikit-learn, it's that scikit-learn is the proper name, but in your code you import it as sklearn. So this is some Python here. If you haven't seen Python before, get ready. If you have seen Python before, you're like, get moving. I'm getting bored, dude. But anyway, so this is the interface for a transformer class. It takes an init method when you can pass in the arguments. And then there's two functions or two methods of each transformer, the fit method and the transform method. And the fit method is where you pass in some new data that you want to set up the transformer with. And then the transform method, you can transform any data. And it's designed for repeated reuse. So you fit once and then use it again and again. And if you're a data scientist already, to explain why you would do this, you fit on your training data and then you reuse the transformer but without refitting it on your testing data. So that way you avoid bias in your test. So hopefully that makes sense to everyone who's heard of this before, and we'll do a real example in just a sec, which should make it a lot more obvious by reviewing listing 510, which was created in the last stream. So sorry if you were on the last stream and this is a boring review for you. I don't know. This is what I do. I got to review, bring people up to speed, because you know how streaming is. You never know who's just dropping in for the first time. And yeah, I've got to assume that people haven't seen this before. So let's look at how some code that actually uses a transformer. I'm not sure I actually... Oh no, I do have it open here. So first I'll show you the code, and then we can talk about how it works. So this is my class. I called it Extreme Scorer because, well, I renamed it actually. If you were on the stream last week, I was using the term fat tails, which is standard in Wall Street. They talk about fat tail distributions a lot. I started thinking that that term wasn't, I don't know, it's just kind of an annoying term. So I just went for extreme scoring because it's more just plain English, especially if you translate this to another language or something. It doesn't really make sense to it's like a cute name that they use on Wall Street. And I'm feeling a little remorseful about using it in the book, but can't change what I did. Anyway, so this is now what I'm calling the extreme scorer. And like in the example, it has an init, a fit, and a transform. And we'll look at what happens in these in just a sec. I'll tell you what this other function here is. This is a wrapper function or a calling function that I use to call the transformer and then use it. So actually, we can show you how this goes. Here I create a scorer using the constructor. Here I call fit, and here I call transform. And now I get the scores back. Then the rest of this listing is just saving. Here I save the score result and crucially also save the transformer. So let's step through this and we'll see how this, I explained what the scoring algorithm is. Hopefully that was reasonably clear. And if it's not, we're about to go through it. So here I have these preset configurations, too many of them, as you can tell. But one of them I know is already the one that I want. Here we go, Extreme Score Transformer. I actually gave it a sensible name, not my usual habit. So, let's go. Let's see what happens when I hit this breakpoint and when I hit this coffee. Okay, so once again, let me check. The data set is this SocialNet 7 dataset 2, the same one I was using before. This is the usual data loading. I already showed it earlier in the stream. And now I'm actually going to create my transformer. And let's go in. I'm giving it one parameter here, which is the skew threshold, which is the threshold for applying the log normalization. And if you look here, there's another default parameter that I didn't pass, which is the Kurt threshold. That's short for the kurtosis, which is, as I mentioned, a measure of how extreme the distribution is. So there's not really too much in this initializer here. As you can see, I set the arguments to what is passed in, and then I set a bunch of values to none, and that's like the whole constructor. And that's typical, I think, for a constructor on a transformer. You're just passing in some arguments, setting stuff up, because the real setup of the transformer happens when you call the fit function. So what do you need to do when you call the fit function on new data? you need to figure out which metrics you're going to apply the log transforms for. I don't know if I made that clear on the earlier slide, but you don't necessarily log transform everything. You can just log transform the metrics which really need it. So let's go into that rather than just talking about it. So now I'm in the fit function of the same file. Let's see, the first thing I do is drop the column which is the outcome. In this case, that's the churn column, but I pass that as a variable or a configuration in case you have a different data set. So what we do is take note of what columns are in the data that we're using, and that's by copying the column values. Now, I need all these measurements to properly do the transformation, and each one of these is going to be like a vector or series of the results. So this is the minimums of each metric, the means, the standard deviations, the skews. Let's look at one of those so you see what I mean. Now these are all getting saved away as member variables, which you may remember I pre-declared. So if I view this as a series, you can see that this is a named vector, which has the mean value of each metric, just like in the summary statistics we saw before. In fact, if you remember that first one, 89.34, that was in the earlier summary stat. So we're just using similar trick here, but I'm storing each one of these vectors again. Now the next thing I have to do is figure out which columns are skewed. So I'm going to use the skew transform, which is the log transform, and then also which columns are extreme. Those are ones that are have high kurtosis, but not the skewed ones. So the skewed, what I call the skewed ones, are those they have to be greater than or equal to 0, which covers a lot of the columns. And then the really extreme ones have high kurtosis. So now, this selects a series of booleans is what happens on this next line. This is currently a list that has true and false for which ones are skewed and which ones are not skewed. With this next line in the code, I'm going to, line 39, I'm going to select only the ones that are skewed and only the ones that are fat-tailed. So now it's a list of only truths in each case. Let's see, we can look at that again real quick if I find it. Yeah, so now it's only truths, and we just dropped the false ones. All right, the next thing I have to do is actually do the transformation with the logs and calculate the means and standard deviations of those columns. You know, I guess I didn't really have to do it up here. I'm just going to redo it. I should actually think about this. I'm thinking of actually a way to improve this now. Because, like I said, I drop the outcome column for now. So I copy the data, I drop the outcome column, and then I go through the skewed columns and I calculate the log of each column and replace the original column with that, or 1 plus the log. And then I recalculate the mean for that column. But I'm starting to think, actually, I should have just not calculated the means earlier. Like, why am I doing this twice? So I just wrote this listing last week, or this code last week. So I guess I'm looking at it again, and I'm realizing things that I did not do that efficiently. But so you do this for all of the skewed columns, and then, that's why I have a breakpoint here to get out of that loop. I already had that set. So then I do the extreme data transformation, which is that hyperbolic thing, which is the value plus the square root of the value squared, that whole thing. And then I retake those means here. But I really just decided that I should do this better. I think I'm going to do it, actually. What do you guys think? Should I finish running through the listing, or should I just like hit the stop button and start over with my proposed improvement? All right, let me just get through the listing. So this finishes the fit function by transforming transforming the training data or the fitting data and then calculating the means and standard deviations on the transform data. I think we're going to get out of the fit function now. All right, the transform function, which we can now apply to any piece of data, any data set we get, is reapplying that transform. Some of it, we're just redoing what we did in the last one here. Copy the data, drop the churn column. Here, this is a checking step where I make sure that the columns in my new data match the columns in the original data. And this is important if you're doing your own transformer or something like this, because when someone reuses your transformer, you don't know if they're going to give you the data you were expecting. So this at least makes sure that all the columns in my original data are present in my new data. And in this next line, line 63, I actually drop any other new columns, and I reorder them if necessary to the right order. Now I apply the skewed transform, logarithm of 1 plus the metric, to the skewed columns, and now I apply the extreme data transformation, that hyperbolic thing, to the fat tail columns. And then I do the subtraction of the mean and dividing by the standard deviation. So lastly, I re-add the outcome column, assuming that it was present in the first place. And then I return it. And that finishes using the transformer. And the rest of this listing is just saving the scores and also saving the transformer. That's not so interesting. So I'll just let that run out. Now I want to go back and make my improvements. So sorry for just hacking this live, but this is part of the fun. Did you see what was inefficient in this code before? Let's go back and just look at the fit function. What is inefficient is that I calculate these means and standard deviations here, and then I don't really use them. But then I go and recalculate them here. So what I've for the transform columns, which has ended up being most of them. So I really practically end up taking the means and standard deviations twice. And you might be like, who cares? It doesn't take that long. And you're right. For this size data set, this is not a problem. But, if you had a lot of data, like 1 million examples or 100 million, this would be kind of stupid and wasteful. So what I really should do is delete these two and just move the calculation of means and standard deviations, down like this. And I think this should work. This should work just as well, if not better. I'm just going to do a quick test of this. Just by hitting that run button. First I'm going to see if this crashes. It says it worked. Now I have to do a quick check of my data to make sure. And the first thing I'm just going to do is eyeball. This is my output folder, which you set in the environment. I'm just going to do a quick eyeballing of this output data. It opened up in my other screen here. This is what I'm looking at. I just want to make sure this looks right in terms of all the scores. The real check is to recalculate the stats on the scores and make sure it has 0 mean and 1 standard deviation. So I'll just show that really quick because this is an important, well, it's not that interesting to do it, but the fact is, if I'm going to change this listing, I'm not just going to change the listing, run it, and walk away without at least testing it, or I might, that's just bad development practice. So I want to do a quick test, and I know that all I need to do is rerun the stats on my score file, which I already have set up here in chapter 5. I'm just checking which version it is. This is the configuration behind the book listings. Yeah, I want to do this version 11. Oh yeah, dataset scores. I think that's actually right. Yeah, so this will run the stats on the dataset scores. It's actually what I ran. Whoops, now I'm running the wrong thing again. I'm going to go down to this run stats. I think I did this in the last one. And that's why. So it's running listing 5, saving else churn, dataset 2 scores, summary stats. Okay. So that's me rerunning the summary stats on the new scores data that I just generated. And hopefully, if I did this right, my score summary stats actually, oh, it looks wrong. All right, I fucked something up. Should I fix this now? Oh God, you guys are gonna like stop watching me. The mean is not 0 in the set 2 scores summary stats. And what did I do wrong then? Let me go back and stare at this listing. Did I just break it when it was right? I feel like what I did is right. Oh no, I see what I do have a bug. See, this is why I checked it. I was too quick. I need to do, this needs to be S. See, you guys didn't stop me. No one was watching. I made a bug and no one stopped me. Duh. I need to actually now take the means on the transformed data. That's what I need to do. Yes. Okay, let me try this again. I'm going to rerun the transformer over here. And then I'm going to recheck the stats, and that will hopefully be correct. So it's quick to run the transformer because the data is not that big. Here's my stats. Let's see. I need to close the old stats file. Live hacking, the hazards of live hacking, when you like try to do something that should be easy and then it screws up. Let's look at these now. Okay, this looks right. Here we go. So now what we can see in the transformed data is the means are all very close to 0. Those are, basically rounding to 0 here. It's scientific notation, so small. The standard deviations are 1. And also, if we look at the skews and kurtosis measurements, they're also all now pretty small numbers. The skews are all well below 3. Wow, one still does have a big kurtosis here, even after the transforms, but that's not too bad. Okay, so now I've actually correctly improved my listing. Thank you for bearing with me there. There was a first little taste of a live hack that was supposed to be just a review, but now I've also done some live coding to improve my transformer from last week with only one bug, so not too bad. Cute song. It looks like a little Pac-Man ghost, of course. With a face, or with snaggletooth and an eye. Alright, we're going to do something new after I get that cough drop in my mouth. Okay, so that finishes the review of transformers from last week, and now we'll do a new kind of transformer. Yes, Crumble Blossom. Troubleshooting is a key skill in data science. And the good sense to just check your work is the key skill. Like, I had the temptation to just like change that code and be like, look, it's done. But fortunately, I went back and did a sanity check to make sure that it worked. All right, let's talk about dimension reduction. That is using fewer metrics, basically. You reduce the dimension. It's also called using fewer features, or it's fewer columns in the data matrix. Now, why do you use fewer columns in the matrix sometimes? Because you have correlated behaviors that customers do. And you can have a lot of metrics. Like in my toy problem, I call it a toy problem because the simulation only has like 8 different events. So there's only about 15 different metrics. In a real product or service, you could easily have 50 or 100 different events, and you could have dozens and dozens of metrics. But many of them are going to be correlated, and that just leads to unnecessary information overload. So I'm going to review correlation between behaviors and talk about the dimension reduction algorithm that I teach in the book. And then we'll actually do it as a transformer. So that's kind of the game plan for the next hour or so of the stream, for those of you who last with me. So first, it's going to be kind of a review, because I've streamed about the dimension reduction algorithm before, but I need to go over it again before I talk about the transformer. Hey, didn't we already hear this song, or is that the band, Screen Time Evolution? Well, I think it's just randomly doing my, one of my favorite copyright-free Twitch music streams on Spotify. Okay, so let's first talk about what is correlation and dimension reduction. I'll do kind of like a quick review. I'll try to keep it to like 10 minutes. Although in the past, I've done an entire stream on this. So if you're like, WTF, this is too fast, you can always check out the other stream. All right, so correlation measures the relationship between behaviors. And I'll show you some real data examples from case studies. This is a company called Clipfolio. So they have a lot of events called Clip. And this is showing two metrics that are almost perfectly correlated, 0.98 correlation. And so when you plot them in a scatter plot, they're very close together in a narrow ellipse. Few outliers, but not many. This is an example of 0.88 correlation from another data set. So it's less correlated. It's kind of like your ellipse is blurring out. This is an example of 0.75 correlation. So your ellipse of points is getting blurred out. This is from a data set that has domestic and local calls for a telco. So what this is showing is that people who make a lot of calls tend to make a lot of domestic calls and vice versa. So that shows those two behaviors are highly correlated. If you were working with them in analysis, you might want to, reduce the dimension by not using all of them. This is a lower correlation, 0.57. This is even lower correlation, 0.31. And this is 0.18 correlation, still a little bit correlated, some tendency for one metric to increase with the other. Now, that's great for looking at pairs of metrics, but it's better to summarize correlations with a correlation matrix. And that's another quick listing we can do. Listing 6.2. This is, again, a review listing that'll only take a minute. Although I'll have to basically make or find a configuration for it. Probably the easiest thing to do is duplicate this one. Call it correlation matrix. I want to do chapter 6, listing 2, I said. I need to check the version that has the new data set, or the big data set. So here this is me checking the configuration for the book, which is in a JSON. Sorry I didn't prep this in advance, but hey, I got a life too, All right, I want to use version... Wait a second. I don't even see the one that I want. Why is there no version of this? I'm going to make a new version for dataset 2. So this is how you modify the configuration for my book. You copy paste and then change it. I'm going to make version 3. I want to use dataset 2 scores, which is the scores we just created. So now I'm going to go back to my configuration and I'm going to enter version 3. And I'll put a breakpoint in the listing to step through it. Kind of sweet tune, kind of gross album cover. It looks like a bloody heart and stuff, but kind of catchy. I'm a sucker for catchy tunes. So this is the correlation matrix listing. It's super short, so let's just hit it. Once again, loading the data. Now this is the score data that we just created. So if you open it up, you'll see that instead of having like normal metric values, it has the small score values all close to 0. But anyway, doing a correlation matrix is really easy. Like everything with pandas, you just call the core function. This is it, CORR. This makes another little data frame, which is a correlation matrix. We'll look at it more closely in a minute. And then I just save it. So this is how we save a correlation matrix, very easily. And I like to save them and look at them saved out, because in a spreadsheet like Microsoft Excel, which I happen to have, it's just easier to look at the rows and columns. Let's see. So the first thing you do when you look at a correlation matrix in a spreadsheet is freeze the rows and columns. This is actually the key advantage over viewing. You could make a correlation matrix to look at and just like save it in a PNG, because we're going to make a heat map. That's what I'm actually doing here. But when you do it in a spreadsheet, it has the great advantage that you can freeze the rows and columns to kind of like cruise around and look at stuff more clearly. So this is showing the correlation matrix. Actually, let me do one more little formatting here, which is turn these to simple numbers, because all correlation values are between -1 and 1. Okay, so now here is a correlation matrix, which we can actually zoom in at and look at. So this is showing that correlation, whoa, too zoomed in, between each of the metrics. So here we can see ad view per month and ad view per post are correlated at 0.46. Ad views per month and likes per month are more correlated at 0.66. That's pretty highly correlated. And what else is highly correlated? Some of these things down here. So let's see. Unfriend per month and unfriend per new friend also correlated. Posts and likes correlated. So it's a little bit hard to see. It's kind of all messy. Wouldn't it be great if the highly correlated metrics were organized together? Let's think about that. We'll be doing that in just a minute. But I just wanted to illustrate what the correlation matrix is and how we calculate one, because this is going to be key in the dimension reduction algorithm we're going to use, because we're going to try to group together correlated metrics. That's the algorithm we're going to do. I don't actually advocate dropping metrics to reduce the dimension, although in some situations you should if you have a lot of metrics. But if you have a moderate number and you believe they're all relevant to your customers, I actually say that you can group together the highly correlated metrics. So that's why we were looking at correlation. And this is what I mean by grouping together highly correlated metrics. And this is a toy problem demonstrating the use of what you call a loading matrix to group the metrics. So this is a toy problem example. Suppose we had 3 metrics that were highly correlated: login, read, and reply. These are not exactly the metrics from the data set. And then you had these other metrics which were correlated: write and send. And then one more metric which was not correlated. So if we're going to group together these 3 metrics, what we do is average them by multiplying them all by 0.33 and then adding them up. So for this first customer, if we average together 0.4, 0.8, and 1, we'd get 0.7. And that would be like our score for these 3 metrics combined. Same trick here, but we're indicating the weights for the average on another line of the matrix, of the loading matrix. And in this case, because there's only 2 to average together, we use 0.5, 0.5. So here this customer 1 has minus 1.6, minus 1.4, they get minus 1.5. All right, so that's a quick walkthrough of averaging data together with a matrix. And we're going to get to the 2 questions are, how do you decide on this matrix, and how do you, well, use it? How do you apply it? I'm kind of illustrating the application of the loading matrix, and I'm going to do that first, and then I'm going to explain how we come up with such a matrix in the first place. You know, I think I bullshitted when I said that this review would only take 10 minutes, because that was like 10 minutes ago. And now I'm still explaining it, but it'll probably take me another 5 or 10 minutes to explain it, and then we'll get back to the coding. So bear with me and enjoy the music. Okay, so this is a toy problem illustrating using a loading matrix. This is actually my illustration of a real loading matrix, and I like to include this slide to explain why do you really do this, because I mentioned that in a real data set you can have a lot of metrics. This data set has, I'm showing 50, but there's actually many more. This was about a 75 or 80 metric data set, or 80 features. But what you see here is that the first 28 metrics were all highly correlated in the correlation matrix. And these were all metrics having to do with dashboard views and edit. This is in a product called Clipfolio that I did a case study on. And then there's this other group of metrics, the group 2, what I call it here, the template gallery metrics. Group 3 are metrics having to do with data source functions, and group 4 is API calls. So these are identifiable groups of activities that customers take. And yeah, so there's just information overload. Like, you don't need all 28 of these metrics about dashboard viewing and editing to understand churn, because they're going to be very related. So this is meant to be like a motivation of why we actually do this. Okay, so let's look first at how you apply the loading matrix. I'm going to run this listing 6.3. Let's see, which I'll have to make a new one for again. Let's see, how am I going to do that? Let's look in here. I'm not really set up for these, for demonstrating these. But I can also, once again, apply loading matrix. All right, listing 6.3, and we're just going to look at how the dimension reduction process unfolds. Let me just check my configurations again. 6.3. You know, I'm not sure we have the. I want to have the version on the data set we're using here, which I actually didn't include in the book. Because at this point in the book, I was still working on the old data set. So, oops. So making a new version of Chapter 6, Listing 3 here. What did I say? Version 2? You guys keeping me honest? I might actually have to calculate the loading matrix first. You know, I have to do listing 4 first, although I like to explain listing 3 first. So let's just look at that. Chapter 6, listing 4. I'm going to set them both up, and then we'll run through them both. Finding metric groups. Let's see. Making another configuration here. Once again, sorry for not actually preparing this in advance. I'm a bad live streamer, but you're learning how to hack your own configurations in my book. If you are a user, these are good skills to have. So now I'm also going to run this. Okay, almost ready. Sorry, bear with me. And then we'll be running code in just a second. I guess this is just version 1, right? All right, first I'm just going to run the, the metrics group. I'm going to show you the algorithm for finding the groups in a minute, but first I'm going to show you the algorithm. Oh no, it's crashing. Oh shit, I did this. Hold on, bear with me, bear with me. You must try to save metric scores first. Why is it not finding? Actually, maybe I'm just supposed to list it by the original name here. That's probably it. Let's try that. Alright, so now I've actually run the metric grouping to calculate the loading matrix, and I'll show it to you in a second. Let's just get into... We're going to look at how to apply the metric groups first, which we're doing right now. It looks like this one also needs to just point to data set 2. Or maybe not. Yeah. This one should also just apply to data set 2. And then it's implied in the code that you need the scores. All right, let's look at, sorry for that diversion. Now we're going to look at how you apply the loading matrix to reduce the dimension. So hopefully I'm going to load the score file that I previously saved. And it's going to say, okay, now I'm going to load the score data. Okay. So this is the score data, or it should be, that we looked at before. Yep. And now I'm going to show you using the loading matrix. This is the loading matrix for this set of data, and it's going to look kind of like the example that I showed you in the slides. Whoops, that's not it. That's the path. Let's look at the loading matrix itself. Oop, it's not defined. Oh, I haven't loaded it yet. And also it's named loadmatdf, of course. Alright, so this will be what the loading matrix looks like for this data set. And it's shown sideways from the example I showed you previously in the slide deck. So, but this means that the first 3 metrics are averaged together because they have non-zero entries. And then the next 2 metrics are averaged together. And then the next 2 metrics are averaged together. But these other ones are just left single. That's why they only have a 1 in each column. You might wonder why these are not 0.33, 0.33, 0.33. And that's a kind of technical subject that I get into in the book. That we don't just do a simple unweighted average, it's a kind of a weighted average that works to improve the normalization of the scores after you've averaged them together. And that's why this is 0.62, 0.62 and not 0.5, 0.5. It's essentially overweighting to increase the standard deviation. Hey Carl, I smoked so much meat and I'm really high and I'm eating a donut. Lord Mushroom 69. Yes, welcome to the data science stream. How is learning data science after smoking a lot of weed, Lord Mushroom 69? Now, I never do that myself, let me just say. And I certainly never do it before I live stream, because that would probably be a pretty bad idea. But maybe I should try it sometime. So thank you, Lord Mushroom 69. And please enjoy the music and the pretty pictures of the data. You see blue numbers. This has got to be a first on my stream, but thank you for... It is late. You know, the thing is, what time zone are you in, Lord Mushroom 69? Because it's only 3 in the afternoon where I am, but for all I know, you know, you're just getting back from a rave in London or something, and whatever works, you know? Oh, you're East Coast? Okay, well, you know. Hey, 6 o'clock, that's cool. Sounds good to me, but I'm going to keep on talking about the data. So this is the loading matrix, and now the key steps here is first to reorder the data to the same order as the loading matrix, or it'll be all messed up. And that's what I do in this line by using the loading matrix index as the list to reorder the columns. If you don't, this is Pandas data frame stuff. You use the bracket, and if you give it a list of strings, I'm also turning it to a NumPy array here. And then actually to do the dimension reduction, this is, whoops, don't want to block it with a pop-up, but this is actually the dimension reduction line because I do a matrix multiplication. And in just a second, I'll show you how matrix multiplication is actually reducing the dimension. But this is it. This is how you load a file, load the loading matrix, and then you just do this matrix multiplication. And now, if you look at the churn data, whoops, that's grouped, well, you can see it first here. Let's see, churn data grouped. Where'd it go? Why aren't I seeing this? Maybe I'm the one who's been smoking too much weed, or maybe my development environment is just messing with me. Oh no, I have to hit one more line. That's why I don't see it. Maybe I have been smoking the weed, Lord Mushroom 69. So anyway, now this is just standard pair programming. Whenever anyone's watching you code, you mess up. That's kind of a given. But so you can see the churn data group has 12 columns, and the original data to group had 16 columns. You can see that here. So we have done the reduction that I talked about. In this line, I add back in the churn column. So now here is my group data. And you can see my first 3 columns got renamed to metric group 1, metric group 2, metric group 3. And then I have the other columns. So that is how, and the rest of this is just saving. So that is how you do, whoa, this song is a little bit crazy. Sorry, Lord Mushroom 69, you might want to cover your ears for this one. It's kind of like grating. I don't usually skip tracks, but I think that one just needed a little skip. It was kind of like making me nervous. So let's see, this one will hopefully be more chill. So that is the code that actually applies the grouping. Let's look at how we find the grouping. That's a little bit harder. Although actually first, this is a quick explanation of how matrix multiplication is used to do the averaging. This is an example. This is like the toy loading matrix we looked at before. So we only have 0.3, 0.3, 0.3 in the first column, 0.5, 0.5 in the second column, and then other zeros. And the key thing is that when you do matrix multiplication, you multiply the column by the row. So these 0.3s multiply the first 3 metrics and give you this number. And the zeros multiply the second 3 metrics, send, write, and like, and don't contribute. And then in the next one, the zeros make it ignore the first 3 metrics, and the 0.5s multiply the next 2 metrics. So, and the matrix multiplication gives you a result with the number of rows, the dimension of your result is the number of rows in the first matrix and the number of columns in the second matrix. So that's why the loading matrix determines the number of resulting columns in the final matrix. So this is an example of why we use matrix multiplication there. All right, this song I guess I can live with a little bit. It's not all my favorite music on these copyright-free channels, but hey man, I got to appreciate. Hats off to the copyright-free music creators that let me stream to something. Alright, so that's why we use matrix multiplication. Now the key question, how do you find the groups? And this is the key part of the transformation step, or the dimension reduction, because I told you it's easy. So you work, it's easy to apply the metric groups. It's a little bit involved to find them. But I like to show the applying the metric group part first, because it kind of motivates, like, why are we trying to find a loading matrix in this way in the first place? So you use hierarchical clustering, or I use this. I prefer this. This is my preferred method. Some people will use principal component analysis, but it's much less interpretable. I have that in my previous stream on this subject about how you can do this with PCA, but it's a lot less interpretable than using my method, which is hierarchical clustering. So in this method, you identify 2 most correlated metrics, and you merge those 2 metrics by replacing them with the average, and you update your correlation matrix. You update your loading matrix, you recalculate the correlation, and then you repeat so that you lose correlated metrics as you go. And my next set of slides has a toy example of this, I believe. Okay, yeah, here's the toy clustering algorithm, example 1. So suppose we have the most correlated metrics are reply and read. So we make these entries in our loading matrix, and then we apply that loading matrix to the data. So it averages those together, and now we get read and reply are averaged as one metric, and then we look for the new highest correlation. In this case, it'll be with login. So we make the first entry in the loading matrix to have 3 entries, and then we do the multiplication to reduce the dimension. That's the other reason I like to show you how to apply the loading matrix before finding it, because a key step of finding it is applying it, as we're showing here. So then the algorithm continues. Now we've got the first three metrics grouped. We find the next highest correlation, which would be between send and write, and we enter that into the loading matrix. Tongue twister here. And then we have this as our new correlation matrix, and the toy clustering algorithm would end because all of these remaining correlations are low. So you group together the high correlations, and then, well, you just keep going like many algorithms. You keep going until you hit a termination condition. And then in the toy problem, this is the loading matrix we would end up with. Okay, this is some better. Wait a second. Listen, Lord Mushroom 69, this is for you. I think he's saying keeps me high. That's what I'm hearing. All right. So let's look at the group finding algorithm. I just made the configuration for it. And I can close this up. Let's see, done with this one. Gotta close up. I got too much stuff open here. Man, I got everything open. The requirements, what the hell? All right. Let's really look at this algorithm now. This is more involved than the first one that applies the loading matrix. Another reason why I show finding the loading matrix second. So this is pretty involved. Let me get to the entry point right down here. It's called find metric groups, and I'll put in a breakpoint. And we'll just go through the main points here. I think Lord Mushroom 69 is no longer with us. He's probably gone on to a more stoner-friendly stream. I don't know. Some people do like to code and do data stuff. HIGH. I don't know. Oh, wait. Wrong listing. I'm not HIGH, but still. Easy to, like I say, easy to make mistakes pair programming. Let's see. So I want to, what did I just do? Correlation matrix, apply loading matrix, calc metric groups. This is what I want to do. Okay. So now I should stop at that breakpoint. I think I did. So I start by reloading the scores, as always in these listings. Drop the churn column because it's not part of the grouping. Check the metric columns. Okay, this is like checking what the columns are. I'm not sure where I use that later. So this first part is actually the key step. This is where you find the metric groups. So let's step into this one. Now, I've got a spoiler alert. Where am I? Oh, I don't want to step into that. Whoops, I stepped into this correlation function. Let me put a breakpoint and find correlation clusters, and we'll go to it. That'll be easier than stepping through all that other code. So spoiler alert, I don't actually use the algorithm that I told you. Remember I just told you about this whole algorithm? This whole thing? I was kind of bullshitting you for intuition. Not really bullshitting, but I don't actually use that algorithm. I use a pre-written algorithm, which is the hierarchical clustering package in SciPy. So we've got scipy.cluster.hierarchy, import linkage and fcluster. So that's what we're going to use. That really does this algorithm under the hood. It does it a little bit differently than the intuitive method that I told you. But it's basically applying that algorithm. Hey, I want to develop. This is PyCharm, which is my preferred IDE. I think it's from IntelliJ, right? PyCharm, about PyCharm. It's my preferred IDE. Community editions. This is free, of course. Some people like other things, but you know, I've been using this one for a while, so I'm used to it. And it's open source, you know, and they got a free community edition. So let me show you how we actually do the hierarchical clustering. The first thing is I convert the correlation. This is the correlation matrix that we calculated earlier. So this is a correlation matrix like the one we looked at a few minutes ago. And I convert it to a dissimilarity matrix by subtracting it from 1. So normally the highest correlation is 1, which is the most similar. And now that will be 1 minus 1, 0, would give you 0. That becomes the most dissimilar, or the least dissimilar, rather. The least dissimilar. This is a little bit confusing, even without Lord Mushroom 69. And then if you had the most dissimilar in a correlation matrix would be -1, and that actually becomes 1 minus 1 is 2. So this subtraction inverts the correlation matrix, which is like a similarity measure, into a dissimilarity measure. And then I just call this linkage function, which actually is what does the correlation. It's kind of all there. I just did the clustering. Did you see it? I'm not going to go into what that linkage function does, but it determines how close together all the metrics are in terms of similarity and dissimilarity. And now the only thing I have to do is apply the threshold, which is my correlation threshold. So I explained the threshold in terms of correlation. So I'm saying, okay, metrics above 0.65 should be correlated. I mean, should be grouped. And then I turn it into a dissimilarity threshold, again, by subtracting it from 1. And then I call the fcluster function. And that actually finishes the grouping. I now have the grouping in terms of these labels, which is just like a list of the group assignment for each metric. So this is saying metric 0 is group 1, metric 1 is group 2, metric 2 is group 1, etc. So that's not exactly what I want. So the rest of this the rest of this algorithm is going to be actually turning this into the loading matrix. Now, so I have these labels. The first step is this algorithm I call relabel the clusters. I'm actually not going to go into that really. But this gives me a column, a matrix showing me what all the columns were before. Holy shit. Am I losing power? Something just happened. Man, am I still live? Wow. I think I'm still live, but I just had like a temporary blackout. Did anything happen? Can people still see me on the stream? It looks like I'm still live, but that's pretty freaky. All right, I'm just gonna keep going and pretend nothing happened. Nothing happened. All right, you guys can still see me, or hear me. Thank you. All right, well, that was weird. Okay, so I was showing you what I have in this labeled column df. It's basically showing what the columns are, and this is the count of how many metrics are in each group. It's actually not that interesting. But I use these now to make the loading matrix as the next step, which is what happens here. Hey, this is I know this song. Who sings this in the non-copyright free version? Don't want to go off the deep end. I know this song though. Good song though. Hopefully this is a good cover or good remix. And I hope it's really copyright free so they don't mute my stream. Anyway, we make an empty loading matrix, and then in this loop, we actually fill it out. This is actually pretty involved. Let's see. This is finding the original column, and basically here's where I set in the loading matrix the entry, which is 1 over the number of... It's like the averaging function, but this is actually how I calculate that weight. I'm not going to go into that too, because this is just supposed to be a quick review. Let's just like kind of fast forward. This is all explained in more detail in the book and in another stream, but I want to actually get on to doing this with a transformer. But so this is all what's involved. This is all adding the column names here. So now I've actually made it into the loading matrix data frame, and hopefully this will start to look like the result that I want. Okay, it's looking like my loading matrix, but it's still unordered, right? I'm getting the entries in there. And now I guess I'm going to do the ordering. I actually haven't looked at this code for a while myself. But yeah, so I set the name column to the index, which I already had. Here I'm sorting the column into the order of the groups that I want. And then this last part is where I actually sort the rows of the loading matrix to keep the groups together. And I'm doing this by using sort values with a sort order that will get them all together. So let's see, now this should look like my final loading matrix. And sorry for going through this kind of quick. I did go through this in gory detail in another stream, and now I wanted to just kind of review the algorithm, and then I want to re-implement it in a transformer. That's where this is really all going. This is going somewhere. So now this really looks like my loading matrix, which I wanted. And that's the next part of this algorithm. And the last bit is just saving. So this just saves out the loading matrix. Not too much happening here. And that's it. And you can see that it says saving the metric groups and saving the loading matrix, and those go to the output directory. Okay, so that is that whole algorithm, and this is all stuff that's in the book, and I previously did a stream devoted to explaining it. So that's kind of like my quick summary here. Now, back to our scikit-learn transformer. It's the end of my coffee for the stream. From here on in, I have to do it on my own energy alone. So I want to take, in my original book, I wrote that as two separate algorithms. And I mean, in case you're wondering why I didn't use the transformer pattern when I was writing the book, it was because, well, I didn't know about it that well, and I was really busy writing the book. The truth is, when I wrote the book, I was translating all this work from R into Python, because at my job, I actually was doing this with R. And then when it was time to write the book, I was like, well, Python's more popular. I better, write my book in Python. So I was doing a big translation exercise. All the original research, had to switch it over to Python. And, I wanted to teach the algorithms to people, which I really see my book as teaching methods, not particular code. So then later on, I was like, oh yeah, I know transformers are a really cool way to do this in Python. I should upgrade the code to use transformers now, now that I have so much free time. So the next thing I want to do is convert that dimension reducing transformer pattern into a transformer and use it. And so I need to basically have an init method, a fit method, and a transform method. And so I think pretty clearly the fit method is going to be based on the last listing I showed you, which was the one to find the metric groups. And then the transform method will be the earlier one I showed you, which was applying the metric groups. But I'll put them all in one package now, which will make it more reusable for later. So this is finally where we've all been going with this stream, which is to do some live coding, which is always more fun than just talking. I did do a little bit of bug fixing in this stream and demonstrating code, but now I'm going to do some live hacking, which is making a transformer to replace those two separate listings. So going back to my code, I'm gonna make a new chapter 6 listing that's not in the book. Basically, that's what I'm gonna do. That's what I do in these streams. I'm basically supplementing the code in the book at this point. So I'm just gonna say a new file, and this will be. They have to follow the pattern. Listing 6.6. What am I gonna call it? I call this metric grouping in the book. I don't call it hierarchical clustering because that's kind of like a mouthful. So I guess I'll call it metric group transformer. Yeah, I guess that'll work. And yeah, I'll add it to my Git. And I need to have I think the way this works is I have to have metric group transformer as a top level wrapper function to call into. And I'm going to need the parameters. Let's close this up, which is the threshold, right? I need the same parameters here because these still apply. And this is basically a new way to achieve the listing. And now I need to get that scikit-learn transformer pattern into my code and modify it to what I actually need. So let's see. I think I should actually, the easiest way to do that might be to honestly just hack into my slide here. I'm just gonna hack into my slide, copy that. Here, I'll go back to presentation mode. And I'm just gonna copy paste that into my file. So now I have the template for my transformer. And what should I call the transformer? I think I'll actually call it hierarchical. I hate, it's such a big word. Hierarchical clustering dimension reducer. Damn, that's a mouthful. Anyone have any ideas for a smaller name I should be using here? Hierarchical cluster. How about I could just say hierarchical cluster dim reducer. That's just a little bit less of a mouthful. So here, now I can take this and go, just to make my code happy, I'll say transformer equals hierarchical cluster dimension reducer. I'll have to pass in that threshold. That's my only argument. I'll need to load the data also. I'd better just copy that from one of my earlier listings. Look, how convenient. It's right here. So basically, let's see. I'm going to load up this data here and do that first. I'll have to import OS. So let's see. If anyone has any tips or suggestions here, feel free to shout them out on the chat. Now I want to develop, I'm just noticing your comment, GL and HF. I am actually not sure on those acronyms. I guess I'm not texting enough people nowadays. Well, let's see. So then we do, here we will call transformer.fit and pass it the score data. And then we'll say reduce data equals transformer.transform, also on the score data. So that's what my final, function is going to look like. I'm going to load some data, I'm going to create the transformer, call the fit, and call the score methods. Now I have to figure out what actually to put in those methods, but it should be pretty close to the code we looked at earlier. Let's go back to that now. So for here we need, let's say self.thresh. The argument has to be the correlation threshold. Core thresh. Maybe I should call this core thresh, and then I can also do remember there's a dissimilarity threshold, 1 minus core thresh. I'll write that out here for clarity. Now, I think that is most of what I need to do in the init. I'm trying to think if there's anything else that needs to happen. let's look back at the find metric. Let's close that actually, don't need that. If we go back here, now these are basically, the thing is, I basically need to do exactly the same thing as here. So what I should practically do is just copy paste, because I already kind of showed you all these functions. So I should probably copy paste these and use these as the basis for my new algorithm. Because remember, what I'm really doing here is just a repackaging of the existing logic. I don't want to change my algorithm. I just want to package it in this object. So I think I'm gonna copy these three functions, and I'm just gonna make. I'm gonna have to modify them for sure. What I'm gonna do is I'm gonna put them in here as helper functions. And obviously I'm going to have a lot of errors because I just copy pasted a bunch of stuff in. So the first thing I need to do is put self in here, because these are class or member functions rather. And I'm also going to prefix them with underscore. Hey, Night of Dark 94. Holy shit, a data scientist who streams data scientists on Twitch. Hey, I'm glad that made your Saturday. Oh wow, and you subscribed too. Well, welcome Night of Dark 94. I am one of the few, the proud, the data science streamers on Twitch. We do exist. Crazy few that we are, but thanks for joining me and glad to have you with us. Let's see, so I'm doing this. I'm actually really not doing data science today. Confession. Maybe I shouldn't tell you, it'll drive you away. I'm coding a data science algorithm that I've already been working with. And I'm actually refactoring a bunch of procedural code into an object using the transformer pattern in scikit-learn. So that's what's happening here. Let's see. And I am a real live data scientist for my day job, which is also why I'm not a very good streamer. I don't stream very much. Hey, if you look over my shoulder, you could just see my dog walking by behind the door, but never mind. So I'm not a very good streamer because I do have a full-time job as a data scientist, which this is why I do this on Saturday, by the way. So let's see. So I prefix these with underscores because that's kind of like the Python convention for private methods or things that you don't want people to call. Wow, this is completely freaking out. What do I need to do here? Why does it say class? I think this is supposed to be self. All right, now let's get into fixing these methods to make them work with the class instead of the code that I copy paste them from. The first thing is this one no longer needs a. This is going to be this is actually going to be the self.disthresh that I already calculated. Now these errors are from missing imports. So I'm going to go back to the code that I copied this from and copy over the imports that I need to my new listing. This is just completely cheap copy paste stuff. Let's see. Why do I have so many imports here? I guess I copied those from my example. These are the things I actually need. So let's see. So this is that find correlation clusters function. No more red errors, so it's looking better. Now, what's happening in relabel clusters? Hey, that seems to have taken care of all the errors there too. Alright, so those errors were just from the imports. So now my fit function in the object is going to look a lot like the old main function. Oh wait, Night of Dark 94 says, you read my bio. Pretty neat. Oh, you're an IT manager. over a monitor engineering team, and you build analytic dashboards and ML models for anomaly detection. Oh, cool. What anomaly detect? Is that a product? Because my company is actually, well, I should tell you, we've already kind of chosen an anomaly detection product. We're using Anomalo. I don't know if you know them. And your goal is also to be a chief data scientist one day. Right on. Well, technically, at my new job, I'm only the senior data science manager. I kind of took a title demotion on my last job, but it's a really cool job, and I'm effectively the chief data scientist, because the chief scientist at my company is like the Stanford professor who was a founder, but he doesn't do it anymore. But he's still nominally the chief scientist, and it's hard to compete with a Stanford professor. So I'm currently a senior data science manager, but whatever. I don't like to be too attached to titles. It's more about doing cool work and getting well compensated for it. So do what you got to do. Anyway, so working on this. But yeah, Night of Dark 94. Let me know about your anomaly detection. Is it an internal project or a product you guys sell? Because we're buying from anomalo.com. Yeah, titles are blah. And you use Splunk. Okay, that's interesting. I'm trying to remember. I know about Splunk, but I haven't used it for a while. But anyway, so let's see. I think I need to basically copy all of this stuff into my new fit function. That's what I was going to do, right? And I never actually did that. So this should pretty much be the content of fit now. But this has to become X, big X. Let's see. And this has to be self._ find correlation clusters. This has to be self_. Sorry, I'm really just refactoring the code. So that's why I said earlier, this isn't a super data science-y stream. I'm actually refactoring my data science work, which is important for those of you, who are not like professionals. You write a lot of code and you really do have to clean it up sometimes. So that's pretty much what's happening here. And this is going to be, well, I'm not passing this as a variable anymore. Let's see. And okay, and make load matrix. I also don't need the threshold, right? Is this the correlations or the thresholds? I think this is the threshold. That's what it's looking right here. So I actually want to replace this with self.coreThresh. See, is it being used in more places? Whoops. That was not what I wanted to do. What I want to do is actually get rid of this as a parameter and then do my search and replace. All right, and then I'm not passing this as a parameter. Now here, I think the key move I need is to save this as a load_mat_df. And now this is going to complain that I'm not declaring it. So I actually want to declare that up here. Self.load_mat_df. And that's actually the key data that that we're producing here. So we're going to initialize that to none. And basically the result of the fit algorithm is that I'm going to end up with this this creating the loading matrix, basically. Let's see, now is all this code going to work now that I've refactored it? This should also be a self. I'm also going to save that, pre-declare that in the constructor. Also equals none. And then I can also stop passing it around. So see, the code gets a lot cleaner now that I'm doing it object oriented. And that should give me an error here because I just deleted it. Let's see, also removing that here. So just replacing the parameter with the member variable. As I go through, boy, I sure use that one a lot. Boy, this is some feel-good music. It just makes me want to smile. But it's good for coding, you know? You need something upbeat to code to. Alright, so that goes away. This is actually definitely better. This is tighter, because now I'm only really passing through the things that we need. Maybe I'll pull this out here. I don't know if we need to store that. That's actually an interesting question. Should we store a correlation matrix? It's not a lot of data, but I'll just pull that out here. I think this actually looks okay for the fit method, assuming I haven't introduced any bugs. So now, I'm going to try to copy over my transform method from my previous code, which I called apply metric groups. And this is the dead simple one, where basically, alright, I need to get this, I need this. This has to go somewhere. Let's see, where's my new one? What should I do? Maybe I should just do that here. I mean, why not? Just save it in both formats. Although, actually, maybe... Sorry, I kind of dropped the mic there. I just sort of smacked the mic. I don't know if that was really loud. Maybe I should just save the ND array. Honestly. I'm kind of like changing my mind here. Oh. Missing an underscore there. So let's make the member variable the ND array, which seems a little bit cleaner. Okay, boy band, run and hide. Nice one. Thank you for making copyright-free music, whoever you are. So, okay, now let's get back to implementing the transform. I basically need, these are the two key lines, and here I'm just, let's see, got to deal with the churn column too. But this is basically what the fit function should be doing. This is going to be, now this is X, that's my new data to group. Although I have to deal with it if there's a churn column. This is going to be, oh wait, now I do need the data frame. Oh, now I'm wishing I kept the data frame. All right, I'm going to keep the data frame too. It's just easier, and it's not that much to store. Because the loading matrix is very small. It's just a small matrix, as you saw. It doesn't really matter that it's a data frame. It'll only take a few kilobytes or something. So now, what do I need to do? Because I was using the index of the loading matrix here. And now here I actually do the grouping. I wonder if there's a better way to do that. Maybe I should just save out the index values. That might be the better approach, but I don't know. Let me just keep going with what I'm doing. I keep using, well actually I need the columns and the index, so. Now here's the problem about I have to deal with this stuff about the isChurn column, which I haven't really dealt with. And I think I should follow the pattern that I was using in my earlier transformers, which is to define in the arguments the outcome column, because it takes special handling in that you need to pull off the outcome, do your transformation, and then put the outcome like back on it at the end. Gonna have another cough drop now, going on 2 hours streaming. Haven't completely lost my voice yet, but hanging in there. So let's see. Actually want to look at my transformer from last time. How did I do it here? Because it's good to be consistent. I want to have a consistent interface for all these transformers. So here, yeah, I pass the outcome column in the constructor, and I default it to isChurn. I'll just save that here. Again, like any good coder, I like to copy paste rather than write new code. Just always be careful. You copy, paste, and then modify if necessary. My first manager as a job when I was a programmer after college. I was a programmer before I did a PhD or did a data science thing. But my first mentor in programming, I always remember he told me, this was Tom Kinch. So Tom, if you're out there, I still remember your words when you said, don't forget, Carl, copy, paste, and then modify. Haha. All right. So now I have to deal with the outcome column, which means probably in the fit method, I need to probably drop it. Let me do what I did in my old listing again, just copying my old stuff. Here I say, if outcome column is no, I'm going to drop it. Else, let's see. So we'll just follow this pattern here. And I'll call this, well, I'll call it data to fit. I don't know, like data to measure so much. Now this has to be, I have to replace x with data to fit in the rest of this function. So that, okay, but we only want capital X. All right. So that's how I'll start out. So now when I do the correlation and find the loading matrix, I'll have dropped the outcome column if there was one. So that's important for getting this right. And now when I transform, oh God, I should make another, I want to like refactor this. Def drop outcome self x. I'm just gonna like move this up here so I can reuse it. Return data to fit. Now here I'll say data to fit equals self dot underscore drop outcome. Wait, but where do I get the outcome? Well, it's actually not important for this fitting, right? But let's see. I'm actually going to give this thing return outcome, call that false. And so now I'll say if not return outcome, else I'll return the data and the outcome. Just doing a little, so now in this one, where I'm going with all this, there is a method to my madness, I hope, or maybe I'm just mad. Here I want to do something similar, and I will also, but I'm going to return the outcome here. This is return outcome equals true. Okay, so Do you see where I'm going with this? Because I need, when I'm fitting, I can just drop the outcome and forget about it. But when I'm transforming, I do need to put it back on at the end. So I'm trying to prepare for that. So now, this is the data to fit. Let's do this. Anything else? Okay, now this is where I would actually use that outcome, because I'm not assuming it is churn. Now I say if self.outCall is not none. Whoops. Now I'm going to reattach the outcome column using it by name. Self.outCall equals, here I'm just calling this outcome. But you know what? I should use lowercase here. Why am I using camel case? That's weird. I use camel case or sentence case in a lot of stuff, but sometimes I forget that in Python I'm supposed to do everything with, you know, lowercase and underscores for actual variables. Which is of course the Python convention. So now let me look at what I've got. You know, I do have a bug here in that outcome column could be none. Here I'll just say out equals, this is what I need to do. This is if there is an outcome column. And this will be out equals none. So I have something to return either way. Or wait, actually this case I don't have to do it. Actually, no, that's unnecessary, right? Or no, well, I don't know. You could call it with return outcome when you had not provided an outcome column. Maybe I should check for that, but let's just keep moving. Let's also replace these. All right, so let's see how I'm doing here. This does the matrix multiplication. This recreates it. This re-adds the outcome column. Now I think I've actually done it. I'm not quite sure. I don't know if anyone watching on the chat thinks I've done it or not. A lot of love songs on this mix. Hope everyone's feeling like lovey-dovey out there, but I guess it's popular for dance clubs to sing about love, right? Right. I don't know if it's so good for coding. So, no, I don't want to return X here. I need to return, obviously, the result. That was like one big bug I was still having. I think this looks okay, actually. The only thing else I need to do is save the result, which I previous did in listing 6.3. I want to save the result. So I'm just going to do it the same way I did it before. And that I do back in the calling function. Now this is just called reduce data. And now the one other thing I do need to do here is actually save my transformer, because that's the key thing about this approach, is that once you save the transformer, it has the knowledge embedded in it to use it again. And so that I can also copy the code I used from my previous transformer that we looked at earlier. Sorry if whipping through all this code is making you dizzy. But I swear, we did go through this listing earlier in the stream, so I don't want to like redo it again. Like I said, any good programmer, we copy paste a lot. Let's see. This is going to be HC dim reduce transform. How about that? Because it's a hierarchical clustering transformer. What did I call it? Yeah, I called it hierarchical cluster dim reducer. So that looks okay. Oh, and I need to import this joblib stuff for the saving. And if you ask me, why do you use joblib to do the pickling and not pickle? The answer is, I don't know. And I never looked it up. I just saw in examples that this is what you use for saving a transformer. Let's call it transformer. So I think this is it. I think I've actually done it now. And now it's time to debug and check. Check my work time, see how I did. Because I'm running this through the Fighting Churn With Data framework, I need to make a new configuration. I showed you this configuration briefly earlier in the stream, but it's a JSON file broken into chapters and then listings. And because I made a new listing 6, I basically need to make a new entry here, list 6. And I need to give it some parameters, which should basically be the same as listing 4, I think. Yeah, I think I can really just reuse, well, I have to change the name. So I copy pasted, now I need to modify that crucial third step of coding. Copy, paste, then modify. And now it should be metric group transformer. And I still need that threshold parameter, and I still need a data set. And, maybe I should just, well, anyway, I guess I'll just make this version 1. That means the version 0 is going to be for the smaller data set. But this version's a little bit more interesting, so I'll keep going with that. Alright, so I made a configuration in the JSON. Now I need to call it. And this will be, I'll duplicate once again, metric group transformer. So now this will be chapter 6, listing 6, also version 1. And yeah, okay, I should be ready to debug, unless anyone has seen any bugs that I've made, and you need to alert me to any bugs that you've seen. This is pair programming, remember. The people who are not coding in pair programming always catch the bugs, not the coder, right? So that means you guys are supposed to be keeping me honest here, but let's just see what happens when I hit the debugger. So far, so good. Okay, load the score data. Again, this is not part of the transformer. Actually, this is already a mistake. Okay, first bug is that in my original listing, I dropped the churn column from the score data, but now I do that in the transformer. So I'm stopping the program, deleting that line, and starting over. Yeah, so here, I mean, this should be a pretty short and sweet function, because all the real smarts is in my transformer class. All right, starting over. First bug fixed. Okay, load the data. Create the transformer with a correlation threshold I passed in. Outcome column I left to the default for the book, but I'm putting that in there so whenever anyone wants to use this on their own data that has a different outcome column name, maybe just good old-fashioned Y, you can still use this. Okay, successfully created the transformer called the initializer. Now let's see how I did with the fit method, because this is like the key part here. Now I'm going to use my new function of dropping the outcome. Let's just see if this works. I have an outcome column, so now I actually drop it, and I also am going to well, I'm checking what the outcome is, but I'm not returning the outcome. So now I'm just returning the data, which should just be the regular old data with the churn column dropped. Looks good. Let's see. Funny lyric. I'd rather be drinking alone. I guess it's rather drinking alone than with one particular person. Most people would rather drink with someone else, unless I guess you're maybe addicted or something. All right, check the columns. That's calculate a correlation matrix. Still need to do that. Take a quick look. Make sure this looks like a correlation matrix. Looks good. Looks good. Now this is actually the clustering part. Dissimilarity calculation, and now I called, those were the two lines that actually did the clustering algorithm. Sorry, you blink and you missed it. That was the actual clustering. All of this is just kind of boilerplate and wrapper code for that one part. But I'm returning my labels as before. And this is supposed to pre-process the label data. Let me just check this. If you were watching the stream 45 minutes ago, I ran the original version of this, so you know what it's supposed to look like. And this is really just a refactoring, which is why I'm kind of going through it quick. Now the key call is creating the loading matrix. So now let's see if the loading matrix has been correctly created. And yeah, it looks like a proper loading matrix. This is the one we saw earlier, if you were watching. So refactoring going as planned so far. And then here I also make it into an ND array. Okay, and I survived my fit function, so I think my debugging is going well. And now I'll actually transform the data. In this case, I'm reusing it on the same data that I fitted on. Seems a little redundant, but this is the proper pattern. So now again, I'm going to drop my outcome. And here, now my outcome is actually real data. And my data to fit is there. Okay. So now I just do this thing with converting my fitting data to a NumPy array, and I call the matrix multiplication. This is getting into one of those slightly too hyper songs, you know. It's a little bit I don't know. We'll see. It looks like it's wrapping up, so I don't have to skip it. All right, and that actually did the grouping with matrix multiplication. Let's make sure this looks like a proper grouped data frame. Okay, it doesn't have the right column names. That's one thing I'm noticing. Does that come next? Oh yeah, now I oop, did I just crash? Oh, I think I'm crashing. Oh shoot. Alright, I was doing so well. Hit a bug. Let's see what happened here. At the console output. Okay, run blah blah blah. What's the problem? Score data is not defined. Okay, I'm calling on the wrong thing. Oh, index equals. Ooh. Okay, this would be. Okay, data to fit dot index. This is copying over the index column from the original data. All right, I was doing good. I'm going to put a breakpoint here and get back in there. And I think this live hack is almost done. All right, skip this to my next breakpoint. Okay, this is where I crashed before. I was basically had my result and I was turning it back into a data frame, which I've now done, I think. Let's take a quick look. Yep, metric group 1, 2, 3 looks correct. And now I have to re-add the outcome column, which should be no problem. Okay, then I return it. And the rest of this is just saving. Let's see if I got it right. save the group score data. Now I'm actually going to save my transformer as a pickle. And that should be it. So I think this has worked. Let me just look in my output directory, and I should see a pickle. So the entire transformer is saved in this 7 kilobyte pickle. I hope you can see that. There we go. That makes it a little bit easier to read. And then this is my data, a big CSV, which I think is also pretty good. So, hey, that's actually pretty good. That didn't take too long. I think I'm good on this. And what I need to do next is to reload the transformer and reuse it. Because right now I created it, I fit it, and I used it, and then I dumped it. But I was only reusing it on the fitting data, so I haven't really achieved too much more than my original code. But I have refactored the algorithm I showed you to the transformer pattern of having a fit method and a transform method. So just to review, let's see, where the heck am I? I think I'm in the wrong file. This is the one we want to look at. So now I have a hierarchical clustered dimension reducer. We have a fit method, a transform method, and these helper functions, which are really the fit method broken down into steps. The transform function, as you may recall, is dead easy, just using a matrix multiplication. Whoops. But so that's it. That is my refactored hierarchical clustering dimension reducing algorithm. And that was my goal for the live hack. So I'm going to declare it done. And I guess I'm kind of done for the day on the stream. I'll just, unless anyone has like any data science-y topics you want to dive into at the last minute. I do like to have live discussions of weird data science topics if you've got them. But if not, I'll just start summarizing what we talked about today. Okay, what is fighting churn? Fighting churn is making targeted interventions with your customers or subscribers. That can include improving your product, engaging with your customer or supporting them, all that good stuff. Metrics summarize customers' events and subscriptions, which we talked about very early in the stream, was the metrics. And then we were using a data set of metrics throughout the whole stream. Now, a transformer is an object encapsulating a data pipeline transformation. That's what we were working on. Now, we also looked a lot at correlation, which is the strength of the relationship between behaviors. And I suggested that you prevent information overload by merging correlated metrics. Now, it's true that in the coding I did today, I was working on a toy problem where it wasn't really necessary. You know, with that little data set of 15 metrics, it's like, why bother reducing the dimension when you only have 15 metrics to begin with? But we did see that a few of them are highly correlated, so they were redundant. And it is really helpful in a real data set if you have 75 or 100 or even 500 features or metrics. Then you really want to use this type of technique and, reduce the number of features or columns in your data. So it's very helpful. And I go over more about why it's helpful in the book. Actually, today you just have to take my word for it that it's actually helpful. Okay, so loading matrix is an efficient way to merge metrics by averaging them using matrix multiplication. So the merge operation scales very well to big data because it's just a matrix multiply with a small loading matrix. And in fact, most of the loading matrix is pretty sparse. So if you actually had big data, maybe you could do a sparse matrix multiplication. So something to think about. Hierarchical clustering is the algorithm that I showed you that finds the groups given a correlation matrix. And then it uses the correlation matrix to figure out, which metrics to group. Let's see. All right, and that's it. So the next stream, I'm going to talk about transformer pipelines, which is a pipeline means that you do one thing after another. So today we looked at two transformers, one for scoring the data and another for dimension reducing it. And in the next stream that I do, I'm going to look at chaining them together, not training, chaining, which means, putting them one after the other in a line or a pipeline. So that's the real power of these object-oriented transformations, which, well, again, I've been streaming for more than 2 hours now. I'm not one of those marathon streamers. It is Saturday afternoon for me, so I'm going to want to, get back to doing some other Saturday stuff. But yeah, if you got any questions about any of this, please shout it out on the chat. Very upbeat music today. I think I probably prefer chill hop for live hacking, but I just went with the upbeat music. Hope it was keeping you awake, kept me moving after my coffee ran out. But so let's see, I'm going to go through with my outro now. Oh, special announcement. There's a new project from my publisher that I created using real data from my publisher. So if you want to actually do your own churn problem using real data and not simulated data like I've been showing today, this is for you. Basically, it's a step-by-step project where you download real data, which is from Manning. Manning has a book reading web service called LiveBook. So basically, you analyze the LiveBook data from Manning, and it's in Live Project is like the product. It's getting kind of confusing, I know, but Live Project is the new project. LiveBook is the Manning data set that you will analyze. You do have to pay for this, and I'm sorry for that. And I don't actually have a discount code for it yet. I should actually ask them about getting a discount code on the stream. And yeah, what else can I tell you about it? It goes step by step through all the different phases of analyzing a real churn data set. So there's 3 sub-projects is what you can kind of see here. In the first one, you actually go from event data to metric data, which I glossed over in this stream, but it's an important thing to learn. The next section, you do churn analysis using analytics. You create a data set, that's actually key, from the metric data. First, create a data set, and then you do churn analysis. And then the third project is doing churn forecasting using machine learning. So probably the third project is going to be the most popular because everyone likes machine learning with a data set. But the first 2 projects are really essential learning if you're going to do this professionally, because in school or in your education, you're just given a data set. Oh, here's a data set, run machine learning. But in your job in real life, you got to make that data set. And that's most of the work. So the first 2 portions of the project are really essential learning, but if you do just want to do machine learning, you can skip to project 3 and you can get the data set for that. So anyway, this is exciting stuff. Yeah, very pleased that this is out there. Manning.com bundles Fighting Churn SER. Let's try clicking on that link. Oh yeah, hey, it works. This is what you'll see. And yeah, Fighting Churn with Manning's LiveBook data. So LiveBook, I can actually just show you real quick. LiveBook.manning.com is this book reading, live service. So in the project, you'll actually analyze the real data from that service. It's pretty cool. All right, enough self-promotion. Oh no, this is more self-promotion. Sorry, people. All right, I live stream every Saturday, 2 p.m. my time. Actually, not every Saturday, but many Saturdays. In fact, I know next Saturday, probably the next 2 weeks, I've got conflicts and I can't stream. But I will be back Saturday sometime, probably 3 weeks from now. Also, if you know any YouTubers out there, or if YouTube is more convenient for you, you can watch all the streams, which I post video on demand afterwards. And of course, you can get the original book from my publisher with a discount code if you want to get it from the publisher and not from Amazon. But like I say to everyone, the reason I do this stream is so that you can learn all this stuff without getting the book. The code is all free on GitHub, like I showed earlier. Back to the GitHub site, Carl24K, Fight Churn. You can get all the code from the book for free and learn all about it by watching the live streams. And please follow me on Twitter. That's where I'll give you updates on my streaming plans. And I don't tweet cat pictures or what I had for lunch or personal opinions. I keep it pretty professional. I stream about data science, churn and subscription businesses are favorite topics for me, obviously. But now that I work at a new startup where I work in a mobile finance application in emerging markets. So now I also tweet about like mobile finance and emerging market startups, which is really cool. There's a huge scene of startups in emerging markets, which I'm part of now. And okay, next stream will be data transformer pipelines, as I said. It'll probably not be for 3 more weeks because I've got 2 different weekend things planned the next 2 weekends. So probably I'll be back in 3 weeks to actually put these transformers together in a pipeline. So, anyone have any parting thoughts on the chat? It's been pretty quiet out there for a little while. Right now, I can do my traditional or habitual check to see if there's any other data or code live streamers that we can raid. I'm like checking it out right now. Let's see. I'm looking if there's any data science coders. There's not that many out there. Ooh, and apparently I got signed out of my out of my Twitch account, so I can't even. So I'm looking for what other live streamers are free right now, and if anyone has a. Hey, thanks Maverick Amit. Thanks for saying it was a great session. I'm glad you liked it. And I'm just checking to see if there's anyone good to raid. Let's see, we could raid game dev, infrastructure. There's very few data science streamers. Like someone joined the stream and was like, oh my god, you're a data science streamer. But yeah, I don't think there's anyone good to raid today. I don't like just doing random raids where I'll just take you to, there's only been 2 times in my entire streaming history that when I finished my stream, there was another data science stream going and I was able to raid it. So today is not going to be one of those days. So I'll just let you go stream some music or, whatever crazy stuff you like to stream. Yeah, I'm going to go probably take my dog for a walk and just do some other random stuff for a Saturday afternoon. So thank you, whatever time zone you're in. Hope you enjoyed it. You learned something cool. Thank you for joining me. Please come back for another stream again. Coldplay cover. I hope it's copyright free or they'll mute my stream as usual. So bye, I'm out. Have a good Saturday. Happy data science. Happy streaming. Until next time.